The James Webb Space Telescope represents one of humanity's most ambitious attempts to peer into the deepest reaches of cosmic time, and what it has revealed since its first observations in 2022 has sent ripples of excitement and concern through the astronomical community. The telescope's unprecedented infrared capabilities allow it to observe the universe as it existed just a few 100 million years after the Big Bang, a period cosmologists call the Cosmic Dawn. What researchers expected to find in this early epoch was a universe still assembling itself, where the first galaxies would be small, relatively simple, and composed of pristine gas clouds slowly condensing under gravity's patient pull. Instead, Webb has shown us something altogether different and deeply puzzling. The lambda cold dark matter model, often abbreviated as lambda CDM, has served as cosmology's standard framework for more than 2 decades. This model describes a universe dominated by 2 mysterious components that together account for roughly 95% of everything that exists. Dark energy, represented by the cosmological constant lambda, drives the accelerating expansion of space itself. Cold dark matter, invisible and interacting only through gravity, provides the scaffolding upon which galaxies and larger structures form. The remaining 5% consists of ordinary matter, the atoms and molecules that make up stars, planets, and living beings. This model has proven remarkably successful at explaining a wide range of observations, from the cosmic microwave background radiation's detailed patterns to the distribution of galaxies across vast cosmic volumes. Within the lambda CDM framework, structure formation follows a specific timeline that can be calculated with considerable precision. Dark matter halos begin collapsing shortly after the Big Bang, creating gravitational wells into which ordinary matter falls. Gas clouds accumulate, cool, and eventually ignite as the first generation of stars. These early stars, composed almost entirely of hydrogen and helium, burn intensely and briefly, ending their lives in supernova explosions that seed their surroundings with heavier elements. Over hundreds of millions of years, this process gradually builds up the chemical enrichment necessary for subsequent generations of stars and the complex structures we observe in today's mature galaxies. The model predicts that truly massive galaxies, containing hundreds of billions of stars and exhibiting the sophisticated features we associate with galactic maturity, should not appear until the universe has aged considerably, perhaps 1 billion years or more after its beginning. Webb's observations have revealed massive galaxies existing at redshifts corresponding to times when the universe was only a few 100 million years old. Redshift, the stretching of light toward longer wavelengths as space expands, serves as a cosmic clock that allows astronomers to determine when the light from distant objects began its journey toward us. Higher redshifts correspond to earlier times and greater distances. Some of the galaxies Webb has detected at extremely high redshifts possess stellar masses comparable to our own Milky Way, which has spent more than 13 billion years assembling its current population of stars. These early giants appear not as small, irregular collections of young stars, but as surprisingly mature systems with well-defined structures, substantial stellar populations, and in some cases, the chemical signatures of multiple generations of star formation. The existence of such massive galaxies so early in cosmic history creates a temporal problem that challenges the lambda CDM model's predictions. Galaxy formation proceeds through a hierarchical process in the standard model, with smaller structures merging to form progressively larger ones. This gradual assembly requires time, both for the physical process of mergers and for the star formation that converts gas into stellar mass. The rate at which stars can form faces physical limits imposed by gas cooling rates, feedback from young stars and supernovae, and the availability of dense molecular clouds where star formation occurs. When astronomers calculate backward from the observed properties of these early massive galaxies, they find that star formation would need to have begun extraordinarily early and proceeded at improbably high efficiencies to produce the observed stellar masses in the available time. Adding to this puzzle, many of these early galaxies display signs of chemical enrichment that indicate multiple stellar generations have already lived and died. Spectroscopic observations reveal the presence of elements heavier than helium, which can only be synthesized in stellar cores and subsequently distributed through supernova explosions. The detection of these elements, sometimes in surprisingly large abundances, implies that a complete cycle of star formation, stellar evolution, and chemical recycling has already occurred. This cycle cannot be arbitrarily compressed in time because massive stars, despite their brief lives compared to lower mass stars, still require millions of years to evolve from birth to explosive death. The chemical enrichment patterns Webb observes suggest these early galaxies possess more complex star formation histories than the simple first-generation populations that the Standard Model predicts. Compounding these challenges are Webb's observations of supermassive black holes in the early universe. These gravitational behemoths, containing millions or even billions of times the mass of our Sun, reside at the centers of most large galaxies today, including our own. The formation and growth of supermassive black holes presents a well-known theoretical challenge even in the local, present-day universe. Black holes grow primarily through two mechanisms: accretion of surrounding matter and mergers with other black holes. Both processes require time, and both face physical limits that constrain growth rates. Accretion cannot proceed arbitrarily quickly because infalling matter heats up and radiates energy, creating radiation pressure that can actually push matter away from the black hole rather than allowing it to fall in. This limitation, called the Eddington limit, means that black holes can at most double their mass roughly every few tens of millions of years under ideal conditions. Webb has detected actively feeding supermassive black holes, observed as brilliant quasars, at redshifts indicating the universe was less than 1 billion years old, and in some cases considerably younger. The masses of these black holes, inferred from the luminosity and spectral characteristics of their emission, reach hundreds of millions or billions of solar masses. Tracing back the growth of such massive objects to their origins creates severe difficulties within the Standard Model. If these black holes began as the remnants of the first generation of stars, with initial masses perhaps a few hundred times that of the Sun, they would need to accrete matter at or near the maximum theoretical rate almost continuously to reach their observed masses in the available time. This scenario requires not only perfect conditions for rapid growth, but also a ready supply of gas in the black hole's vicinity and minimal interference from the feedback effects that accretion itself generates. Alternative formation scenarios have been proposed to explain how supermassive black holes might achieve large masses more quickly. Direct collapse black holes, for instance, could form when pristine gas clouds collapse directly into black holes, with initial masses thousands or tens of thousands of solar masses, bypassing the stellar evolution stage entirely. However, the conditions required for direct collapse are quite specific and probably rare in the early universe. The gas must remain hot enough to resist fragmenting into individual stars, which typically requires intense ultraviolet radiation from nearby sources to suppress cooling. Even if direct collapse black holes do form, they still face the same accretion rate limitations in their subsequent growth. The presence of numerous supermassive black holes at very high redshifts suggests that whatever formation mechanism operates must be considerably more efficient or more common than standard models predict. The rapid formation of cosmic structures extends beyond individual galaxies and black holes to encompass larger-scale organization of matter. Webb has observed what appear to be protoclusters, concentrations of multiple galaxies in relatively small regions of space at epochs when the universe was supposed to be more homogeneous. In the lambda CDM model, structure formation proceeds from the bottom up, with small fluctuations in the density of dark matter gradually growing under gravity's influence. These fluctuations, seeded by quantum variations in the very early universe, are imprinted on the cosmic microwave background radiation as tiny temperature differences. The pattern and magnitude of these fluctuations have been measured with exquisite precision by missions like the Planck satellite, and they place tight constraints on the parameters governing structure formation in the Standard Model. The growth rate of density fluctuations depends critically on the universe's composition and expansion history. Dark matter, which interacts only gravitationally, begins clustering as soon as the universe cools enough for gravity to overcome the expansion. Ordinary matter, initially too hot and ionized to collapse, couples to the radiation filling the early universe and cannot fall into dark matter halos until after recombination, when electrons and protons combine to form neutral hydrogen about 380,000 years after the Big Bang. Even after recombination, gas cooling and subsequent structure formation require additional time. The lambda CDM model predicts a specific timeline for how dense regions evolve into galaxies and how galaxies cluster into groups and larger structures. The detection of well-developed galaxy concentrations at very early times suggests that structure formation may have proceeded more rapidly than this timeline allows. These observations collectively paint a picture of an early universe that was more active, more organized, and more mature than theoretical expectations based on lambda CDM would suggest. The tension between observations and theory has become sufficiently pronounced that some researchers have begun questioning whether modifications to the standard model might be necessary. However, before exploring potential alternatives or extensions to lambda CDM, it's worth examining more closely what aspects of the model might be flexible and what observations could be telling us beyond the simple interpretation that the model fails. One possibility is that the apparent masses of early galaxies might be systematically overestimated due to observational uncertainties or astrophysical effects not fully accounted for in current analyses. Galaxy masses are typically inferred from their brightness using relationships between luminosity and stellar mass derived from studies of nearby galaxies. These relationships depend on the stellar population's ages, metallicities, and star formation histories. Early galaxies might have unusual stellar populations with different properties than those typical of local galaxies, leading to incorrect mass estimates when standard relationships are applied. For instance, if early galaxies contain a higher proportion of massive, luminous stars than typical present-day galaxies, they would appear brighter for a given total stellar mass, potentially leading observers to overestimate their true masses. Similarly, uncertainties in redshift determinations could affect the inferred ages, and thus the apparent tension with theoretical models. Photometric redshifts, estimated from a galaxy's brightness in multiple wavelength bands rather than from high-resolution spectra, can sometimes be ambiguous or incorrect. A small number of the early massive galaxies initially identified by Webb have been found, upon follow-up spectroscopic observations, to lie at lower redshifts than originally estimated, placing them in a later cosmic epoch where their existence creates no particular theoretical difficulty. However, spectroscopic confirmation for many of the most distant candidates has now been obtained, and the existence of genuinely massive galaxies at redshifts above 10 appears secure. While some individual cases may represent misidentifications, the overall population of early massive galaxies seems robust. Another consideration involves the efficiency of star formation in the early universe. Standard models assume that gas converts into stars with relatively low efficiency, meaning that only a small fraction of the gas available in a dark matter halo actually forms stars, while the rest remains gaseous or is expelled by feedback processes. If star formation efficiency were higher in the early universe than these models assume, galaxies could build up stellar mass more rapidly. Physical reasons for enhanced early star formation efficiency might include differences in the properties of primordial gas, which lacks the heavy elements that provide important cooling pathways in present-day molecular clouds, or different feedback mechanisms in metal-poor environments. However, substantially increasing star formation efficiency creates its own problems, including potential overproduction of stars in later epochs, and difficulty explaining why local dwarf galaxies appear to form stars with very low efficiency. The supermassive black hole problem might potentially be addressed through modifications to our understanding of black hole formation or growth, rather than through changes to cosmology itself. If massive black holes could form through direct collapse or other rapid formation channels more commonly than currently thought, their early presence might be accommodated within the standard cosmological framework. Research into these alternative formation channels has intensified following Webb's observations, and theorists are exploring the conditions under which heavy black hole seeds might form. The challenge lies in creating the right conditions frequently enough to explain the observed population of early quasars while remaining consistent with other observations of the early universe and with the properties of black holes in later epochs. For the larger-scale structure observations, one must consider that what appears as a dense concentration of galaxies in projection on the sky might not represent a gravitationally bound structure. Chance alignments along the line of sight can create the appearance of clustering when galaxies are actually separated by large distances along our line of sight. However, spectroscopic redshift measurements for galaxies in apparent protoclusters can reveal whether they genuinely occupy a small volume of space or are merely projected coincidences. In several cases, spectroscopy has confirmed that early galaxy concentrations do represent real overdensities, genuinely clustered structures in the early universe. Even accounting for these various caveats and potential systematic effects, a persistent tension remains between Webb's observations of the early universe and the predictions of the lambda CDM model. This tension manifests across multiple independent observables, including galaxy stellar masses, black hole masses, structural properties of galaxies, and the degree of large-scale clustering. When multiple independent lines of evidence point in the same direction, suggesting earlier and more rapid structure formation than predicted, the cumulative case for a genuine discrepancy strengthens. The scientific community's response has involved both continued observational efforts to refine measurements and reduce uncertainties, and theoretical work exploring what modifications to the standard model might reconcile observations with theory. Modifications to lambda CDM might involve changes to the properties or behavior of dark matter itself. The standard model assumes that dark matter is cold, meaning its particles move slowly compared to the speed of light and have been non-relativistic throughout most of cosmic history. Cold dark matter enables structure formation to begin early and proceed hierarchically from small to large scales. Alternative dark matter candidates with different properties could affect structure formation timelines. Warm dark matter, consisting of lighter, faster-moving particles, would suppress the formation of small-scale structures and potentially alter the timeline for galaxy formation. However, warm dark matter typically delays structure formation rather than accelerating it, moving in the wrong direction to resolve the tension with Webb's observations. Self-interacting dark matter, which experiences forces beyond gravity when dark matter particles encounter each other, represents another alternative that has received attention. These interactions could affect the density profiles of dark matter halos and potentially influence how efficiently gas cools and forms stars within them. However, the observational constraints on dark matter self-interaction are quite tight from studies of galaxy clusters and other systems, leaving limited room for strong effects. More exotic possibilities involve dark matter that interacts with ordinary matter or radiation in the early universe through forces beyond gravity, potentially affecting the timing of structure formation. These scenarios require careful theoretical development to ensure they remain consistent with the wealth of other observations that constrain dark matter's properties. Changes to our understanding of dark energy and cosmic expansion present another avenue for potentially modifying lambda CDM predictions. In the standard model, dark energy manifests as a cosmological constant, an energy density that remains perfectly uniform and constant in time. This causes cosmic expansion to accelerate, with the acceleration becoming increasingly dominant as the universe ages and matter density decreases through dilution. However, dark energy need not take the form of a cosmological constant. More general models allow dark energy's density to vary with time, either increasing or decreasing as the universe evolves. If dark energy behaved differently in the early universe, the expansion history would differ from standard predictions, potentially affecting structure formation rates. A variation in expansion history influences structure formation because the rate at which the universe expands determines how much time density fluctuations have to grow before expansion dilutes them. Slower expansion in the early universe would allow structures to form more rapidly and become more massive for a given redshift. However, changing the expansion history has far-reaching consequences throughout cosmology. The expansion rate affects the age of the universe at any given redshift, the relationship between distance and redshift, the behavior of the cosmic microwave background, and the abundances of light elements produced in the first few minutes after the Big Bang during primordial nucleosynthesis. Any modification must remain consistent with all these diverse observations, which collectively constrain the expansion history quite tightly. When cosmologists encounter observations that challenge standard models, they face several possible interpretations. The most conservative approach involves questioning whether the observations themselves might be affected by systematic errors or misinterpretations. The next level considers whether adjustments within the existing framework can accommodate the new data without fundamentally altering the model. Only when these options prove insufficient do scientists seriously consider revolutionary changes to foundational assumptions. The James Webb Space Telescope's discovery of massive galaxies at extremely high redshifts initially prompted all three responses. Some researchers examined whether photometric redshift estimates might be systematically biased, potentially placing these galaxies at lower redshifts than initially calculated. Photometric redshifts rely on measuring the brightness of objects through multiple filters and comparing these measurements to templates of galaxy spectra. While generally reliable, this method can occasionally produce spurious results, especially when dealing with unusual galaxy properties or limited data quality. Spectroscopic follow-up observations have since confirmed many of the most challenging cases, measuring precise redshifts through the identification of specific spectral features like hydrogen emission lines or oxygen absorption. These confirmations demonstrate that at least some of the problematic galaxies genuinely existed at the early times indicated by their redshifts, eliminating measurement error as a complete explanation. Another question concerns the interpretation of galaxy masses. Astronomers typically estimate stellar masses by measuring the total light emitted by a galaxy and applying assumptions about the stellar initial mass function, the distribution of stellar ages, and the relationship between stellar mass and luminosity. These assumptions derive from observations of nearby galaxies and theoretical models of stellar evolution. If conditions in the early universe differed substantially from those today, these standard assumptions might yield incorrect mass estimates. For instance, if early galaxies contained an unusually high proportion of massive stars compared to lower mass stars, they would emit more light per unit stellar mass than typical present-day galaxies. This could make them appear more massive than they actually are. Some researchers have explored whether variations in star formation conditions might produce such effects, potentially reducing the apparent tension with standard models. However, detailed analyses of the spectral properties of these early galaxies suggest that while some mass estimates might be slightly inflated, this effect cannot fully account for the observed population of massive systems. The galaxies show spectral features consistent with substantial stellar masses and significant chemical enrichment, both requiring extensive prior star formation. Additionally, the number density of these massive galaxies exceeds predictions, even accounting for reasonable uncertainties in mass estimates. The rapid formation of supermassive black holes presents complementary challenges. Quasars powered by billion solar mass black holes have been discovered at redshifts corresponding to times less than 1 billion years after the Big Bang. Growing black holes to such enormous masses within the available time requires sustained accretion at or near the theoretical maximum rate, a process fraught with difficulties. Black holes grow by consuming surrounding matter, but this process contains inherent limits. As material falls toward a black hole, it forms an accretion disk that heats to extremely high temperatures through friction. This hot material emits intense radiation that exerts outward pressure on infalling matter through a process called radiation pressure. When the luminosity reaches a critical value known as the Eddington limit, the outward radiation pressure balances the inward gravitational force, effectively shutting off further accretion. The Eddington limit depends on the black hole's mass, with more massive black holes having higher limiting luminosities. A black hole accreting continuously at the Eddington limit grows exponentially with a characteristic timescale of roughly 40 million years. Starting from a stellar mass seed of perhaps 10 to 100 solar masses, continuous Eddington-limited accretion for 700 million years could in principle produce a billion solar mass black hole. However, this idealized scenario faces several practical obstacles. Real accretion rarely proceeds continuously at the maximum rate. Feedback effects, where energy released during accretion heats and disperses surrounding gas, interrupt the supply of fuel. The accretion disk itself exhibits instabilities that cause variability in the accretion rate. Most challenging of all, growing a billion solar mass black hole requires not just time, but also a sufficient supply of fuel located close enough to the black hole to accrete within the available timeframe. These considerations have led researchers to explore alternative scenarios for black hole formation and growth. One possibility involves starting with much more massive seeds. While stellar collapse typically produces black holes of a few to perhaps 100 solar masses, certain conditions might enable the direct collapse of gas clouds into black holes of 10,000 solar masses or more. These intermediate mass seeds would provide a substantial head start in reaching billion solar mass scales. Direct collapse scenarios require specific conditions to prevent the gas cloud from fragmenting into stars before collapsing into a black hole. One proposed mechanism involves pristine gas clouds that have never been enriched with heavy elements. In the absence of metals, the primary cooling mechanism involves molecular hydrogen, which can be destroyed by ultraviolet radiation from nearby sources. If background radiation suppresses molecular hydrogen cooling, while the gas remains warm enough to resist fragmentation, the entire cloud might collapse directly into a massive black hole. Another intriguing possibility suggests that black holes might occasionally grow through super-Eddington accretion, temporarily exceeding the classical limit. Certain geometric configurations of the accretion flow might allow higher accretion rates by reducing the effective radiation pressure. For instance, if infalling material approaches the black hole primarily from the poles while radiation escapes preferentially through the equatorial plane, the radiation might not effectively impede the inflow. Some observations of nearby systems hint at such super-Eddington accretion, though whether this process could operate efficiently enough and long enough to explain the earliest quasars remains uncertain. The discovery of these early supermassive black holes also raises questions about their relationship to their host galaxies. In the local universe, supermassive black holes and their host galaxy bulges exhibit tight correlations, with black hole mass typically amounting to roughly 0.1% of the bulge stellar mass. This relationship suggests a deep connection between black hole growth and galaxy evolution, likely mediated by feedback processes where energy released by the active black hole regulates star formation in the surrounding galaxy. Early observations of high redshift quasars suggested that these relationships might differ in the young universe, with black holes potentially representing a larger fraction of the total stellar mass. Such findings would indicate that black holes grew more rapidly than their host galaxies in the early universe, with the familiar correlations emerging only later as galaxy growth caught up. However, more recent observations paint a more complex picture, with some early systems following the local relations while others deviate significantly. These variations might reflect differences in formation pathways or evolutionary histories. Galaxies that formed through multiple mergers might exhibit different black hole to stellar mass ratios than those that grew primarily through smooth accretion. The scatter in these relationships at early times could provide clues about the dominant formation mechanisms and the role of environmental factors in shaping galaxy and black hole growth. The broader pattern emerging from James Webb observation suggests that structure formation proceeded more rapidly and efficiently in the early universe than standard models predict. This accelerated evolution manifests not only in massive galaxies and black holes, but also in the chemical enrichment of the early intergalactic medium. Spectroscopic observations of distant quasars reveal that even at very early times, the gas between galaxies contained significant abundances of heavy elements, indicating that multiple generations of star formation had already occurred. The synthesis of elements heavier than helium requires nuclear fusion in stellar cores, with the most massive stars producing and dispersing these elements through supernova explosions. The presence of substantial heavy element abundances at high redshifts implies that efficient star formation began very early and proceeded rapidly enough to enrich the intergalactic medium within the first billion years. This timeline stretches the capabilities of standard cosmological models, particularly given the additional constraint that the first generation of stars formed from pristine gas with no heavy elements must precede these chemically enriched populations. First-generation stars, composed purely of hydrogen and helium, would have exhibited very different properties from stars forming today. Theoretical models suggest these primordial stars could have been extremely massive, perhaps hundreds of solar masses, burning through their nuclear fuel in just a few million years before exploding as supernova. These violent deaths would have dispersed newly synthesized heavy elements into the surrounding medium, seeding subsequent generations of star formation with the chemical ingredients necessary for planet formation and ultimately life. The rapid appearance of chemical enrichment observed by James Webb implies that this process of stellar birth, evolution, and death proceeded swiftly and efficiently. However, integrating these observations with other constraints presents challenges. The explosions of massive stars inject enormous amounts of energy into the surrounding gas, potentially heating it and suppressing subsequent star formation. balancing the need for rapid chemical enrichment with the requirement for continued efficient star formation demands a delicate coordination of processes that may be difficult to achieve within standard frameworks. Cosmologists have begun exploring various modifications to the standard lambda cold dark matter model that might accommodate these challenging observations. Some proposals focus on adjusting the properties of dark matter itself, while the cold dark matter paradigm assumes that dark matter particles moved slowly in the early universe, enabling the formation of small-scale structures. Alternative scenarios consider different possibilities. Warm dark matter, consisting of particles with slightly higher velocities, would suppress the formation of the smallest structures while still permitting the growth of larger ones. This might seem counterproductive for explaining early massive galaxies, but careful modeling reveals potential benefits. By suppressing the formation of numerous small halos, warm dark matter could potentially channel more material into larger structures, accelerating their growth. However, detailed calculations suggest that the warm dark matter particle masses required to explain early massive galaxies conflict with other observational constraints, particularly observations of the Lyman alpha forest, which probes small-scale structure through its effects on quasar spectra. Other proposals invoke modifications to dark matter interactions. While cold dark matter is assumed to interact only gravitationally, self-interacting dark matter models allow dark matter particles to scatter off one another through some additional force. These interactions could affect the internal structure of dark matter halos and potentially influence the efficiency of galaxy formation. Some researchers have investigated whether self-interactions could enhance early structure formation, though most studies suggest the effects would be relatively modest and unable to fully explain the James Webb observations. More radical proposals question whether dark matter exists at all, revisiting modified gravity theories as alternatives to dark matter. These theories, such as modified Newtonian dynamics and its relativistic extensions, attempt to explain observations attributed to dark matter by proposing that the laws of gravity differ from Einstein's general relativity on large scales or in weak gravitational fields. While these theories have achieved some successes in explaining galaxy rotation curves and other phenomena, they face significant challenges in explaining the full range of cosmological observations, particularly the cosmic microwave background and large-scale structure. The James Webb observations do not obviously favor modified gravity over dark matter, as both frameworks must confront the challenge of explaining rapid early structure formation. Modified gravity theories would need to demonstrate that their altered gravitational dynamics enable faster structure growth in the early universe, while remaining consistent with all other cosmological observations. This represents a formidable challenge that has not yet been convincingly met. Another category of proposed solutions involves adjusting the initial conditions for structure formation. In the standard picture, the primordial density fluctuations that seed structure formation are characterized by a nearly scale-invariant power spectrum, meaning that fluctuations have similar amplitudes across a wide range of scales. This prediction emerges naturally from simple models of cosmic inflation, the hypothesized period of exponential expansion in the earliest moments after the Big Bang. However, inflation encompasses a broad class of models with diverse predictions. Some inflationary scenarios predict deviations from scale invariance, with enhanced power on certain scales. If the primordial power spectrum contains significantly more power on scales corresponding to the first galaxies, these structures could have formed earlier and grown more rapidly. Careful observations of the cosmic microwave background constrain the primordial power spectrum on large scales, but smaller scales relevant to galaxy formation remain less certain. Researchers have investigated whether primordial power spectrum modifications could explain early massive galaxies. The challenge lies in finding modifications that enhance early galaxy formation sufficiently without violating other observational constraints. Significantly increasing power on small scales might overproduce certain types of structures or conflict with observations of the Lyman alpha forest or galaxy clustering at later times. Threading this needle requires careful modeling and confrontation with diverse datasets. Some proposals invoke primordial non-Gaussianity, departures from the assumption that primordial density fluctuations follow a simple Gaussian statistical distribution. Non-Gaussian initial conditions could affect the abundance of rare high-density peaks that collapse earliest to form the first galaxies. Certain types of non-Gaussianity enhance the number of such peaks, potentially increasing the abundance of early massive structures. However, current constraints on primordial non-Gaussianity from cosmic microwave background observations limit the magnitude of effects achievable through this mechanism. A different approach questions whether the star formation efficiency in early galaxies might have differed substantially from theoretical predictions. In standard models, the efficiency with which gas converts into stars depends on various factors, including gas cooling rates, feedback from stellar radiation and supernovae, and the dynamical properties of dark matter halos. These processes are complex and difficult to model from first principles, requiring semi-analytic approximations or expensive numerical simulations. Most models predict relatively low star formation efficiency in early galaxies, with feedback effects preventing more than a small fraction of available gas from forming stars. However, if conditions in the early universe somehow favored more efficient star formation, perhaps through different feedback mechanisms or enhanced gas cooling, galaxies could have assembled their stellar masses more rapidly. Identifying physical mechanisms that would produce such enhanced efficiency without violating other constraints represents an ongoing research challenge. One possibility involves the role of primordial magnetic fields. Magnetic fields affect gas dynamics, particularly in the ionized plasma that dominated the early universe after reionization. Strong magnetic fields could alter the structure of accretion flows onto galaxies, potentially affecting cooling rates and star formation efficiency. However, the origin and evolution of cosmic magnetic fields remain poorly understood, and incorporating them into cosmological models involves substantial uncertainties. Another consideration involves the potential role of dark matter annihilation or decay. If dark matter particles occasionally annihilate or decay, they release energy that heats the surrounding medium. In most contexts, this heating would suppress structure formation by preventing gas from cooling and collapsing. However, some researchers have explored whether carefully tuned dark matter properties might actually enhance early structure formation through indirect mechanisms, perhaps by affecting the thermal history of the intergalactic medium in ways that channeled more gas toward collapsing structures. These various proposals share a common feature in that they attempt to work within the basic framework of the lambda cold dark matter model while adjusting specific parameters or adding new physical processes. This conservative approach acknowledges the impressive successes of the standard model while seeking modifications that might accommodate problematic observations. However, an alternative perspective suggests that the mounting tensions might signal the need for more fundamental revisions to our cosmological framework. Some cosmologists have begun questioning whether the assumption of homogeneity and isotropy holds as universally as typically assumed. The standard Friedmann equations that describe cosmic expansion assume perfect homogeneity, meaning that matter and energy are distributed completely uniformly throughout space. In reality, the universe exhibits structure on all scales, from planets to galaxy clusters. But cosmologists typically treat these inhomogeneities as small perturbations around a smooth background. This approximation works well on sufficiently large scales, where the universe does appear statistically homogeneous. Observations of the cosmic microwave background confirm that the early universe was extraordinarily uniform, with density variations of only 1 part in 100,000. However, as structure grows, non-linear gravitational effects become important, and the relationship between the actual lumpy universe and the idealized smooth model becomes more subtle. Most cosmologists treat these effects through perturbation theory or numerical simulations that follow structure growth while accounting for non-linear effects. However, some researchers have proposed that back-reaction effects, where small-scale inhomogeneities collectively affect large-scale evolution, might modify the expansion history in ways not captured by standard approaches. If back-reaction were sufficiently strong, it might even provide an alternative explanation for cosmic acceleration without requiring dark energy. The relationship between back-reaction and the James Webb observations remains speculative. Proponents argue that if inhomogeneities affect cosmic evolution more strongly than typically assumed, this could modify the relationship between redshift and cosmic time, potentially providing more time for structure formation at high redshifts than standard models indicate. However, most experts remain skeptical that back reaction effects are large enough to resolve the tensions, as the effects would need to be dramatic and would likely conflict with other precise cosmological measurements. A more radical possibility involves reconsidering the assumption that physical laws and fundamental constants remain unchanged over cosmic history. The standard cosmological model assumes that quantities like the gravitational constant, the fine structure constant, and particle masses maintain the same values they have today throughout the entire history of the universe. This assumption draws support from theoretical considerations and from the impressive internal consistency of cosmological observations when analyzed under this assumption. However, some theoretical frameworks, particularly those inspired by string theory or other attempts to unify gravity with quantum mechanics, suggest that fundamental constants might vary. If gravitational strength or other relevant parameters differed in the early universe, this could dramatically affect structure formation rates. Stronger gravity at early times, for instance, would accelerate the collapse of matter into galaxies and black holes, potentially explaining their surprisingly early appearance. Testing such scenarios requires identifying observational signatures that would differ from predictions assuming constant physical laws. Astronomers have searched for evidence of varying constants through multiple methods. High-resolution spectroscopy of distant quasars can constrain variations in the fine structure constant by examining the wavelengths of atomic transitions, which would shift if the fine structure constant changed. Analyses of the abundances of light elements produced during Big Bang nucleosynthesis can constrain variations in particle physics parameters at those early times. So far, these searches have found no convincing evidence for varying constants, placing stringent limits on how much variation could have occurred. Any modifications to fundamental constants sufficient to resolve the James Webb tensions would need to be carefully reconciled with these null results. This proves challenging, as the same changes that would accelerate structure formation typically also affect other processes in ways that might conflict with observations. The situation becomes even more intricate when considering potential alternatives to standard dark matter models. Modified Newtonian dynamics, often abbreviated as MOND, represents one attempt to account for gravitational anomalies without invoking dark matter at all. Under this framework, gravity behaves differently at extremely low accelerations, naturally explaining rotation curves of galaxies without requiring invisible matter. Yet MOND has struggled to account for observations at larger scales, particularly the cosmic microwave background and gravitational lensing patterns that seem to require dark matter's presence. More sophisticated variations have emerged, including models that treat dark matter as a superfluid at galactic scales, while behaving like conventional cold dark matter at cosmological distances. These hybrid approaches attempt to capture the best features of both frameworks, potentially offering solutions to the small-scale problems that plague standard cold dark matter while preserving its successes at explaining large-scale structure. Whether such models could also address the James Webb anomalies remains an open question requiring detailed investigation. Warm dark matter presents another alternative worth examining. If dark matter particles possessed higher velocities than assumed in cold dark matter models, they would smooth out structure on small scales through free streaming, potentially delaying the formation of the smallest objects. Paradoxically, this might actually exacerbate rather than resolve the James Webb tensions, since we're trying to explain structures that appear too early rather than too late. However, more complex scenarios involving multiple dark matter components, some cold and some warm, might offer unexpected solutions by affecting structure formation in non-intuitive ways. Self-interacting dark matter introduces yet another dimension to consider. If dark matter particles scatter off each other occasionally, rather than passing through entirely collisionlessly, this could alter the inner density profiles of dark matter halos and affect how efficiently baryons collapse to form galaxies. Strong self-interactions might prevent halos from becoming too dense too quickly, but moderate interactions could potentially enhance certain aspects of structure formation under specific conditions. The parameter space remains largely unexplored, particularly regarding how self-interactions would influence the earliest stages of galaxy formation. Dark matter decay presents possibilities that connect to the tension in other ways. If dark matter particles slowly decay into lighter stable particles, or radiation, this would affect the overall matter budget of the universe over time. An early epoch of slightly higher dark matter density, followed by gradual decay, might alter the timeline of structure formation compared to standard models. However, such scenarios face tight constraints from observations of the cosmic microwave background and large-scale structure at later times, making it challenging to construct viable models that help with early galaxy formation without violating other observational limits. The role of magnetic fields in early structure formation deserves attention as well. Magnetic fields can influence gas dynamics, providing additional pressure support or channeling gas flows in particular directions. If primordial magnetic fields existed at higher strengths than typically assumed, or if dynamo processes amplified fields very efficiently in early galaxies, this might affect how rapidly stars formed and how bright early galaxies appeared. Magnetic fields could also influence the accretion of material onto black holes, potentially affecting their growth rates. The challenge lies in understanding how such fields would originate and evolve in the early universe without introducing new tensions with other observations. Turbulence and small-scale gas dynamics introduce complexities that simulation resolution struggles to capture fully. Gas in the early universe wouldn't collapse smoothly, but would develop complicated velocity structures, shocks, and mixing layers. These features can significantly affect cooling rates, fragmentation patterns, and ultimately the efficiency of star formation. Current simulations parameterize these effects through sub-grid models, but our understanding of turbulence in the unique conditions of the early universe remains incomplete. Better treatment of these processes might reveal that gas can cool and form stars more rapidly than standard models suggest. The three-body problem of galaxy formation involves dark matter, gas, and radiation interacting in intricate ways. Radiation pressure from early stars can blow gas out of small, dark matter halos, potentially preventing or delaying subsequent star formation. However, in deeper gravitational potential wells, gas might remain bound despite feedback, allowing continued rapid growth. The interplay determines which halos successfully form visible galaxies and which remain dark. If the balance tipped more favorably toward gas retention in the early universe than current models predict, perhaps due to different stellar populations or radiation field geometries, this could enable faster apparent galaxy growth. Ionization's impact on early galaxy observations presents another layer of consideration. When the first stars and galaxies flooded the universe with ultraviolet radiation, they ionized the neutral hydrogen that pervaded intergalactic space. This phase transition affected subsequent galaxy formation by heating gas and changing its chemical state. But it also influenced observability. Galaxies forming during ionization would be surrounded by partially neutral material that could absorb or scatter their light in complex ways. Our assumptions about how to interpret observations from this epoch depend on models of reionization that themselves contain uncertainties. The Lyman alpha forest offers clues about intergalactic gas conditions at high redshift. This collection of absorption features in quasar spectra traces neutral hydrogen along the line of sight, revealing the distribution and temperature of gas in filaments between galaxies. Measurements extending to the James Webb era could in principle constrain when and how ionization occurred, which structures existed to produce the ionizing radiation, and what thermal history the intergalactic medium experienced. Tensions between Lyman alpha forest data and models of structure formation would provide independent evidence for problems with the standard picture. The helium abundance adds another primordial constraint to consider. Big Bang nucleosynthesis produced not only hydrogen but also helium, lithium, and trace amounts of other light elements in proportions that depend on the baryon density and expansion rate during the first few minutes. Observations of helium in metal-poor stars and gas clouds generally confirm these predictions, anchoring our understanding of the universe's baryon content. Any modifications to cosmology intended to resolve James Webb tensions must preserve agreement with helium measurements, limiting what changes are permissible to the early universe's history. The lithium problem, wherein observations find less lithium-7 than Big Bang nucleosynthesis predicts, introduces a separate puzzle that might or might not connect to the issues raised by James Webb. Some proposed solutions to the lithium discrepancy involve physics beyond the standard model, such as decaying or annihilating particles during nucleosynthesis, or uncertainties in nuclear reaction rates. If these solutions point toward more fundamental modifications of our cosmological framework, there might exist unexpected connections between the lithium problem and the early structure formation tensions, though no clear links have emerged yet. Gravitational lensing by massive early structures provides an additional observational avenue. If very massive halos formed earlier than expected, they would gravitationally lens background sources, creating characteristic distortions and multiple images. James Webb's deep fields reveal numerous lensed galaxies, and statistical studies of lensing rates as a function of redshift can constrain the abundance of massive halos through cosmic time. Preliminary analyses suggest lensing rates consistent with standard models, though uncertainties remain large. As sample sizes grow, lensing statistics may provide powerful independent tests of whether the massive structure implied by bright early galaxies actually existed. Weak lensing measurements probe matter clustering on larger scales through subtle correlated distortions of background galaxy shapes. Extending these measurements to higher redshifts challenges current capabilities, but will become increasingly feasible as data accumulates. If matter clumped more strongly in the early universe than lambda cold dark matter predicts, this should appear as enhanced weak lensing signals at high redshift. Current measurements don't yet reach the precision needed to detect subtle enhancements, but future surveys may close this gap, providing crucial tests of whether structure formation truly accelerated beyond standard expectations. The kinetic Sunyaev-Zeldovich effect offers yet another probe of early structure. When ionized gas moves through the cosmic microwave background, it imparts a Doppler shift to the photons through scattering, creating a temperature distortion that depends on the gas velocity. Large-scale motions of galaxy clusters produce this effect, and in principle, coherent flows in the early universe would leave detectable signatures. If structures formed earlier and grew larger than expected, the associated velocity fields would differ from standard predictions, potentially revealing themselves through careful analysis of microwave background data combined with galaxy surveys. The cosmic infrared background contains integrated light from all galaxies throughout cosmic history, including those too faint to detect individually. Its spectrum and angular fluctuations encode information about when stars formed, how dusty early galaxies were, and how luminous they appeared. Measurements of this background must account for all galaxy populations, and discrepancies between direct galaxy counts and the integrated background light could indicate missing populations or misunderstood early galaxy luminosities. Current measurements show rough consistency, but refined analyses may reveal tensions that point toward unexpected early galaxy properties. Population 3 stars, the theorized first generation of stars forming from pristine gas without heavy elements, would possess properties quite different from later stellar generations. Their extreme temperatures and high masses would produce copious ultraviolet radiation, possibly creating very bright galaxies, even with relatively modest stellar masses. If population 3 stars contributed more significantly to early galaxy luminosity than typically assumed, this could partially explain bright early galaxies without requiring extreme total stellar masses. However, population 3 stars would also rapidly enrich their surroundings with heavy elements, limiting how long they could dominate a galaxy's light, and observations increasingly suggest early galaxies already contain significant heavy element enrichment. The initial mass function describes the distribution of stellar masses forming from a collapsing gas cloud. In present-day galaxies, most stars form at low masses, with high-mass stars being relatively rare. Theory suggests the initial mass function might have differed in the early universe, with pristine gas potentially favoring more massive stars. A top-heavy initial mass function in early galaxies would produce brighter stellar populations and more energetic feedback, both affecting observational signatures and evolution rates. Constraining the ancient initial mass function remains difficult but crucial for interpreting observations of the first galaxies. Binary stars and stellar interactions introduce complexities often simplified in galaxy formation models. In dense early star clusters, frequent stellar encounters could produce exotic objects like blue stragglers, X-ray binaries, and rapid mass transfer systems. These populations might contribute disproportionately to a galaxy's luminosity or appear in unexpected colors. Dense stellar environments also increase supernova rates and collective feedback effects, potentially accelerating the enrichment and evolution of early galaxies beyond what simulations treating stars as independent entities would predict. The dust properties of early galaxies remain uncertain despite growing observational constraints. Dust forms from heavy elements ejected by supernovae and evolved stars, so naive expectations suggest early galaxies should contain little dust. However, observations reveal substantial dust even in quite young systems, implying either very efficient dust production or alternative formation channels like grain growth in dense clouds. Dust profoundly affects galaxy visibility, reddening and dimming optical light while re-radiating energy in the infrared. Misestimating dust content would bias inferred stellar masses and star formation rates, potentially contributing to apparent tensions. Polycyclic aromatic hydrocarbons represent a specific component of the dust and gas mixture that produces distinctive emission features in infrared spectra. Their presence indicates particular chemical conditions and radiation fields. James Webb's spectroscopic capabilities reveal these features in early galaxies, offering clues about their chemical enrichment and star formation conditions. Surprisingly strong PAH emission in some young galaxies suggests rapid chemical evolution or unusual interstellar medium conditions, challenging simplistic pictures of pristine early systems gradually building up complexity. Molecular gas, particularly hydrogen molecules, provides the immediate fuel for star formation. Mapping molecular gas distributions in early galaxies remains observationally demanding, but increasingly feasible through millimeter and radio observations. The molecular gas content, combined with stellar masses and star formation rates, constrains how efficiently galaxies convert gas into stars and how much fuel remains for future growth. High molecular gas fractions in early galaxies suggest they retained most of their baryons in star-forming reservoirs, potentially explaining rapid stellar mass buildup. The cold gas mass fraction represents the ratio of cold gas to stellar mass in a galaxy, indicating what stage it occupies in its evolutionary sequence. Gas-rich galaxies retain potential for continued star formation, while gas-poor systems have largely finished building their stellar populations. Observations suggest early galaxies maintained high cold gas fractions, remaining in vigorous star-forming states. This differs from local galaxies where various processes have depleted gas reservoirs. Understanding what regulated gas content and star formation efficiency in early versus late galaxies bears on whether we correctly model their growth timescales. Outflows and galactic winds represent crucial regulatory mechanisms that remove gas from galaxies, potentially halting star formation. Driven by supernova explosions, stellar winds, and radiation pressure, these outflows can eject material far into intergalactic space or temporarily suspend it in extended halos from which it might later fall back. The efficiency and geometry of outflows depend on galaxy mass, star formation rate, and environmental factors. If outflows proved less effective in the early universe than currently modeled, perhaps due to different stellar populations or deeper potential wells, galaxies might have retained gas and formed stars more continuously. The mass loading factor quantifies how much mass is expelled in winds relative to the star formation rate. High mass loading factors indicate efficient feedback that can self-regulate star formation, while low values suggest weak feedback, unable to prevent rapid gas consumption. Theoretical estimates and local observations suggest mass loading factors decrease with galaxy mass, meaning massive galaxies eject smaller fractions of their gas. If this relationship held in the early universe, it might help explain why massive galaxies could form quickly. But tension arises regarding whether the most massive systems observed by James Webb could accumulate sufficient mass given cosmic age constraints, even with favorable feedback. Environmental effects on galaxy evolution vary dramatically between dense clusters and isolated field regions. In clusters, galaxies experience ram pressure as they move through hot intracluster gas, stripping away their cold star-forming reservoirs. They undergo tidal interactions with neighbors and may merge more frequently. Field galaxies evolve more quietly, primarily regulated by internal processes. The James Webb galaxies inhabit a universe younger and less clustered than today's, raising questions about what environmental conditions they experienced and whether environmental effects operated differently in that less evolved cosmic web. The two-point correlation function measures how clustered galaxies are in space, revealing information about underlying dark matter distribution and galaxy formation efficiency in different environments. Measurements of early galaxy clustering can test whether the most luminous systems occupy the most massive dark matter halos as expected, or whether something unusual about their formation disconnects them from the typical galaxy-halo relationship. Preliminary clustering measurements of James Webb galaxies suggest consistency with massive halos, but refined statistics may reveal surprises. Protoclusters, the progenitors of today's galaxy clusters, represent overdense regions in the early universe destined to collapse into massive systems. Several James Webb observations have targeted known protoclusters, finding rich populations of galaxies forming in close proximity. These environments might naturally produce numerous bright galaxies through enhanced merger rates and abundant gas supplies. However, this raises questions about whether field galaxies at similar redshifts also show unexpected properties, or if the tensions concentrate in special environments. Environmental dependence could provide important clues about which physical processes enable rapid early galaxy formation. The stellar mass assembly histories reconstructed from observations trace how galaxies built up their stellar populations over time. Comparing these histories to dark matter halo mass growth in simulations reveals whether galaxies grew in tandem with their dark matter halos, or whether stellar mass assembly lagged behind halo growth. For massive galaxies observed by James Webb at very high redshift, their stellar masses imply they assembled substantial populations in the few 100 million years available, requiring almost immediate and efficient conversion of available baryons into stars. This challenges models where stellar mass builds gradually through many generations of star formation and mergers. Satellite galaxies orbiting larger systems offer tests of structure formation on small scales. The abundance and properties of satellites depend on how the smallest dark matter halos form and whether they host visible galaxies. Discrepancies between predicted and observed satellite populations in the local universe, sometimes called the missing satellites problem, hint at incomplete understanding of small-scale structure formation. If similar issues affect the early universe, they might relate to the James Webb tensions, though connections remain speculative. More likely, any solutions must account for both local satellite observations and early massive galaxy observations simultaneously. Tidal streams, the elongated structures created when small galaxies are torn apart by larger ones, provide archaeological records of past interactions. In nearby galaxies, detailed maps of tidal streams reveal accretion histories and help reconstruct mass assembly pathways. Similar features should exist around early galaxies, but detecting them at high redshift pushes observational limits. Future deep imaging may reveal tidal structures around James Webb galaxies, constraining whether they grew through numerous minor mergers or assembled more smoothly, bearing on questions of whether their formation histories follow standard expectations. The concentration parameter of dark matter halos measures how centrally concentrated their density profiles are. Halos that formed early tend to be more concentrated than those forming later at the same mass, reflecting the higher average density of the universe when they collapsed. If James Webb galaxies inhabit unusually concentrated halos, this could indicate they formed earlier than the cosmic time at which we observe them, perhaps pointing toward modified halo assembly physics. However, concentration measurements require detailed gravitational lensing or dynamical data, rarely available at high redshift. Halo spin affects how efficiently gas can cool and form a rotationally supported disk. High-spin halos possess more angular momentum, which gas inherits as it collapses, creating extended disks where star formation may proceed differently than in low-spin systems forming compact spheroids. The distribution of halo spins emerges from tidal torques during structure formation and should follow statistical predictions from simulations. If early halos systematically possess different spins than expected, perhaps due to unusual tidal environments or modified gravitational dynamics, this could affect galaxy formation efficiency in ways not yet fully explored. The assembly bias phenomenon describes how halos of the same mass but different assembly histories cluster differently in space. Early forming halos tend to occupy slightly more overdense regions than late forming halos of equal mass. This subtle effect matters because local environment influences galaxy properties. If assembly bias operated more strongly in the early universe, or if early forming halos dominated galaxy populations more than expected, the typical environments and clustering of visible galaxies might differ from standard predictions, potentially affecting their apparent abundance and properties. Cross-correlations between different traces of cosmic structure reveal relationships between galaxy populations, gas, and dark matter. For instance, correlating galaxy positions with gravitational lensing maps shows how galaxies trace the underlying matter distribution. Similarly, correlating galaxies with Lyman alpha forest absorption reveals how they relate to intergalactic gas. Conducting such analyses at the redshifts of James Webb galaxies challenges current capabilities but promises rich information about whether early galaxies' relationships to their surroundings match theoretical expectations. The three-dimensional power spectrum of galaxy clustering encodes information about initial conditions, dark matter properties, and galaxy formation physics across a wide range of scales. Measurements at high redshift remain sparse and noisy, but continuously improve. If early galaxies cluster more strongly than predicted on certain scales, this could indicate enhanced structure formation, biased galaxy formation efficiency, or unexpected dark matter physics. Current data shows broad consistency with expectations, but statistical uncertainties remain large enough to hide subtle anomalies. Baryonic acoustic oscillations, the characteristic scale imprinted by sound waves in the early universe, provide a standard ruler for measuring cosmic expansion history. Detecting this feature in galaxy clustering at the highest redshifts would both confirm the standard acoustic physics and enable measurements of cosmic expansion at early times. Any surprises in the expansion history or in the sound horizon scale could point toward modified physics. So far, detections of baryonic acoustic oscillations become increasingly challenging at higher redshifts, but next-generation surveys may achieve sufficient precision to test for anomalies. The Alcock-Paksinski test uses the distortion of clustering patterns along and across the line of sight to constrain cosmic geometry and expansion rate. Applying this test at high redshift requires accurate measurements of both angular and redshift space clustering, demanding large galaxy samples with reliable redshift measurements. As James Webb and other facilities build statistical samples, such geometric tests may provide independent checks on whether the universe expanded as lambda cold dark matter predicts, or whether deviations occurred that might relate to the observed structure formation tensions. Redshift space distortions arise when galaxies' peculiar velocities, driven by gravitational infall into overdense regions, add to their Hubble flow redshifts. These distortions contain information about gravity's strength and matter clustering amplitude, measuring redshift space distortions at the highest redshifts tests, whether gravitational dynamics followed general relativity's predictions, and whether matter clustered as strongly as simulations suggest. Preliminary measurements remain consistent with expectations, but improved precision may reveal subtle anomalies indicating modified gravity or structure formation. Cosmic voids, the underdense regions between filaments and clusters, evolve differently than overdense regions and provide complementary tests of cosmological models. Void sizes and abundance depend on the matter, density, expansion history, and gravity's nature. Studying voids at high redshift remains observationally challenging, but offers potential tests independent of overdense regions where galaxy formation complications concentrate. If the early universe's void structure doesn't match predictions, this could indicate problems with the underlying cosmology rather than galaxy formation details. The integrated Sachs-Wolf effect describes how photons from the cosmic microwave background gain or lose energy passing through evolving gravitational potentials. In an accelerating universe, gravitational wells decay as dark energy dilutes matter's influence, imparting a net energy change to photons. This creates correlations between microwave background temperature maps and large-scale structure traced by galaxies. Measuring this effect at different redshifts tests dark energy's history. While the effect operates primarily at lower redshifts, understanding its full evolution constrains cosmological models potentially relevant to resolving James Webb tensions. Neutrino masses affect structure formation by suppressing growth on small scales, as massive neutrinos stream freely through clustering matter. Precise measurements of neutrinos' total mass come from combining multiple cosmological probes, including cosmic microwave background data, galaxy clustering, and gravitational lensing. Current constraints place neutrino masses below about 1/10 of an electron volt per species. If future measurements revealed higher masses or unexpected neutrino properties, this could affect structure formation timescales, though connections to the specific James Webb anomalies remain uncertain. Dark radiation, or extra-relativistic species beyond the 3 known neutrino types, would affect the expansion rate during the radiation-dominated era, changing the cosmic microwave background and the growth of structure. Cosmological data constrain any such additional components tightly, leaving little room for unknown relativistic particles. However, subtle variations within allowed uncertainties might influence detailed predictions for early structure formation. Exploring whether permitted dark radiation parameter space could ease James Webb tensions without violating other constraints represents an ongoing research direction. Primordial non-Gaussianity describes deviations from Gaussian statistics in the initial density fluctuations. Inflationary models generally predict nearly Gaussian fluctuations, but various mechanisms could generate non-Gaussianity that would alter how structure forms from these initial conditions. Significant non-Gaussianity would change the abundance of rare, massive halos, potentially affecting early galaxy and black hole formation. Current constraints from the cosmic microwave background and large-scale structure limit non-Gaussianity to low levels, but some parameter space remains unexplored, and weak non-Gaussianity might still influence high redshift structure formation. Isocurvature perturbations represent a different type of initial fluctuation than the standard adiabatic density perturbations. While observations strongly favor adiabatic perturbations, small admixtures of isocurvature modes remain allowed. These would affect the relative distributions of dark matter, baryons, and radiation differently than pure adiabatic modes, potentially creating unusual initial conditions that could influence early structure formation. Whether isocurvature contributions could specifically address James Webb observations without conflicting with cosmic microwave background constraints requires detailed investigation. Running of the spectral index describes how the amplitude of initial fluctuations varies with scale in a more complex way than a simple power law. Measurements constrain this running to be small but non-zero. If running proves stronger than currently measured, it would change the relative importance of fluctuations at different scales, affecting when and how structures of various sizes form. Careful reanalysis of running consistent with all available data might reveal parameter space enabling faster early structure formation, though any such solutions must remain compatible with local observations. Alternative theories of gravity beyond general relativity propose modifications that could affect cosmic expansion or structure growth. Modified gravity theories often aim to explain dark energy or dark matter phenomena through gravitational physics rather than new substance. Some theories predict deviations from general relativity, particularly at early times or on specific scales. If a modified gravity theory could accelerate early structure formation while preserving successes of general relativity and lambda cold dark matter on other fronts, it might resolve tensions. However, the extremely tight constraints from solar system tests, gravitational wave observations, and cosmological data make constructing such theories difficult. Scalar tensor theories introduce additional fields beyond the space-time metric, allowing gravity's strength to vary dynamically. The most famous example, Brans-Dicke theory, has been largely ruled out by observations, but more sophisticated versions with screening mechanisms survive. These theories can affect cosmic expansion history and structure growth differently than general relativity. Exploring whether parameter space exists where scalar tensor modifications ease James Webb tensions without violating stringent tests from other sources represents an active research area, though no clear solutions have emerged. The equivalence principle, which states that gravitational and inertial mass are identical and that all objects fall identically in a gravitational field, undergirds general relativity. Tests of this principle reach exquisite precision in the solar system and through binary pulsar timing. Any theory modifying gravity to address cosmological puzzles must preserve equivalence principle agreement or explain why violations appear only in cosmological contexts. This fundamental constraint significantly limits possible modifications, making it challenging to construct theories that help with structure formation tensions while respecting equivalence principle tests. Gravitational waves from black hole mergers provide direct tests of general relativity in the strong field regime. Observations so far show excellent agreement with predictions, confirming that gravity behaves as general relativity describes even for massive, rapidly moving sources generating intense space-time curvature. These results constrain alternative gravity theories, particularly their predictions for gravitational wave propagation speed and polarization states. While current gravitational wave observations probe relatively recent cosmic times, future detectors accessing lower frequencies will reach earlier epochs, potentially revealing deviations relevant to structure formation tensions. The speed of gravitational waves, measured to exquisite precision through comparison of gravitational wave and electromagnetic signals from neutron star mergers, matches the speed of light as general relativity requires. This single measurement ruled out entire classes of modified gravity theories that predicted different propagation speeds. The constraint proves so powerful because any modification to gravity that affects cosmic expansion or structure growth typically also alters gravitational wave propagation. Constructing viable theories consistent with this constraint while addressing James Webb anomalies severely limits options. Extra dimensions, predicted by string theory and other fundamental physics frameworks, could affect gravity if accessible at low energies. In such scenarios, gravity might propagate through additional dimensions, while other forces remain confined to ordinary three-dimensional space, potentially explaining why gravity appears weaker than other forces. But extra dimensions could modify gravitational dynamics in ways relevant to cosmology if their size or properties varied over cosmic time. However, current constraints from gravitational observations and particle physics experiments limit such scenarios tightly, providing little room for effects large enough to resolve structure formation tensions. The cosmological constant problem, the enormous discrepancy between the observed vacuum energy density and theoretical predictions from quantum field theory, represents one of physics' most profound puzzles. While not directly related to James Webb observations, any fundamental solution to this problem might involve new physics that also affects structure formation. For instance, if vacuum energy varies dynamically rather than remaining constant, it could influence cosmic expansion in ways that would alter structure formation timescales. Connecting these disparate problems requires speculative leaps, but fundamental physics sometimes reveals unexpected links between seemingly separate phenomena. Anthropic reasoning suggests that we observe particular values of fundamental constants because only such values permit the existence of observers. This perspective potentially applies to cosmological parameters as well. If our universe represents one member of a vast multiverse with varying properties, we necessarily inhabit a region where structure formed successfully. However, this framework struggles to make sharp predictions and offers little guidance regarding James Webb observations specifically, though it reminds us that some coincidences in physics may lack deeper explanations beyond observational selection. The fine-tuning problem in cosmology encompasses various observations suggesting the universe's properties occupy a narrow range permitting structure and life. The cosmological constant's small positive value, the matter-antimatter asymmetry, the initial density contrast amplitude, and numerous other parameters appear carefully balanced. Whether these represent true fine-tuning demanding explanation or simply observational selection remains debated. James Webb's observations of unexpected early structure don't clearly connect to traditional fine-tuning discussions, though they emphasize our incomplete understanding of how the universe's properties emerged. Cyclic cosmological models propose that the universe undergoes repeated cycles of expansion and contraction rather than originating in a single Big Bang. In such frameworks, each cycle might inherit or reset various properties, potentially affecting structure formation in ways differing from standard Big Bang cosmology. Most cyclic models face significant theoretical challenges regarding entropy growth and singularity avoidance. Whether they could address James Webb observations specifically remains unexplored, as cyclic models primarily aim to resolve questions about the ultimate origin of the universe, rather than details of structure formation within a given cycle. Bouncing cosmologies avoid the initial singularity by having the universe contract from a previous phase before reaching minimum size and rebounding into the current expansion. The bounce might involve exotic physics, like quantum gravity effects or violation of energy conditions. Properties of the universe before and during the bounce could set initial conditions for structure formation differently than standard inflation. If such models predicted enhanced initial fluctuations or modified expansion histories, they might account for rapid early structure formation. However, constructing consistent bouncing cosmologies that match all observations while avoiding instabilities proves difficult. The inflationary paradigm itself faces ongoing scrutiny, despite its successes in explaining cosmic microwave background properties and large-scale homogeneity. Various observations, including some related to initial fluctuation spectra and non-Gaussianity, constrain inflationary models. If the true mechanism generating initial fluctuations differed subtly from standard single-field slow-roll inflation, This might produce initial conditions slightly different from typically assumed, potentially affecting structure formation. However, cosmic microwave background observations strongly constrain initial conditions, limiting room for variations sufficient to resolve James Webb tensions. The multiverse hypothesis suggests that physical reality encompasses vastly more than our observable universe, with different regions possessing different properties, including varying constants and laws. While this framework addresses certain fine-tuning questions, it makes few specific testable predictions about our particular region. The James Webb observations don't obviously support or challenge multiverse ideas, as they probe structure formation within our observable domain. However, discovering that our universe's properties differ from what seems natural in fundamental theory might strengthen arguments that we inhabit a special region of a larger multiverse. Experimental searches for dark matter particles continue through direct detection experiments, seeking interactions in underground detectors, collider experiments attempting to produce dark matter particles, and indirect detection efforts looking for annihilation or decay signals. Despite decades of effort, no convincing dark matter particle signal has emerged, though sensitivity continues to improve. Null results increasingly constrain certain candidate particles, like weakly interacting massive particles, in their traditionally favored parameter ranges. If dark matter consists of something more exotic than anticipated, this could affect structure formation in unexpected ways, though connecting laboratory searches to cosmological observations remains challenging. Axions represent particularly well-motivated dark matter candidates arising from solutions to the strong CP problem in particle physics. These extremely light particles would behave differently than typical cold dark matter candidates, potentially affecting small-scale structure through quantum pressure effects. Axion dark matter models predict characteristic signatures in structure formation and in certain astrophysical systems. Whether axion properties could address James Webb observations while remaining consistent with other constraints requires detailed modeling, with research ongoing into how axion dark matter would influence early galaxy formation. Primordial black holes, formed from density fluctuations in the very early universe rather than stellar collapse, represent another exotic dark matter candidate. If a substantial fraction of dark matter consisted of primordial black holes, this would dramatically affect structure formation, as black holes gravitationally attract and potentially accrete surrounding matter differently than particle dark matter. Various observations constrain primordial black hole abundance across different mass ranges, generally limiting their contribution to dark matter. However, certain mass windows remain less constrained, and recent interest has focused on whether primordial black holes could account for some black hole merger events detected through gravitational waves. The quantum nature of reality might influence cosmology in ways not yet fully appreciated. Quantum mechanics governs the behavior of initial fluctuations generated during inflation and the properties of fundamental fields. Some researchers explore whether quantum effects at cosmological scales could influence structure formation or cosmic evolution beyond what standard classical field theory treatment captures. While highly speculative, such quantum cosmology approaches might reveal unexpected connections between fundamental physics and large-scale structure that could bear on observations like those from James Webb. Emergent gravity proposals suggest that gravity isn't fundamental, but arises from more basic microscopic degrees of freedom, analogous to how thermodynamics emerges from statistical mechanics. In such frameworks, gravitational dynamics might deviate from general relativity under certain conditions, particularly in cosmological contexts where emergent descriptions might break down or behave unexpectedly. These speculative ideas remain far from established theory. But if gravity does emerge rather than being fundamental, the implications for cosmology could be profound and might conceivably connect to puzzles like rapid early structure formation. The holographic principle, emerging from black hole thermodynamics and string theory, suggests that the information content of a region scales with its boundary area rather than volume. Applied to cosmology, holographic ideas lead to surprising connections between cosmic expansion and quantum gravity. Some researchers explore whether holographic constraints affect structure formation or cosmic evolution, potentially limiting how quickly information theoretic or thermodynamic quantities can grow. Whether such deep theoretical principles could manifest as observational effects relevant to James Webb discoveries remains highly uncertain, but represents intriguing theoretical territory. String theory, the leading candidate for quantum gravity, predicts various phenomena potentially relevant to cosmology, including extra dimensions, moduli fields, and cosmic strings. While most string theory effects manifest at energy scales far beyond observational reach, some might influence cosmology. String cosmology scenarios explore how the universe might have evolved through phases involving stringy physics, potentially setting initial conditions for the hot Big Bang differently than standard inflation. Whether string theory insights could illuminate current observational puzzles remains an open question as theorists work to extract testable predictions from this mathematically rich framework. Loop quantum gravity, an alternative approach to quantum gravity, treats spacetime as fundamentally discrete at the Planck scale, with geometry built from quantum loops. This approach makes predictions about the very early universe, suggesting that quantum gravity effects might prevent the initial singularity and lead to a bounce. Loop quantum cosmology explores these ideas, predicting modifications to the early universe's evolution that could affect initial conditions for structure formation. Whether such modifications would help with James Webb observations requires connecting the fundamental quantum gravity theory to effective descriptions relevant for structure formation, a challenging task still underway. The measurement problem in quantum mechanics asks what causes quantum superpositions to collapse into definite outcomes. While usually considered in microscopic contexts, some researchers explore whether measurement-like processes occur in cosmology, potentially affecting the universe's evolution. Objective collapse theories propose that quantum states spontaneously localize under certain conditions, which might influence cosmic fluctuations. These ideas remain speculative and controversial, but they illustrate how unresolved questions in fundamental physics might unexpectedly connect to cosmological observations. Complexity theory and self-organization principles might offer insights into how structures emerge from simpler initial conditions. Complex systems often exhibit emergent behaviors not obviously predictable from microscopic laws. While galaxies ultimately form through gravity acting on density fluctuations, the detailed pathways involve intricate feedbacks and nonlinear processes that might generate complex, emergent phenomena. Whether complexity theory frameworks could predict unexpected regimes where structure formation accelerates beyond naive expectations represents an underexplored interdisciplinary direction. Information theory provides languages for quantifying the information content of cosmic structures and how information flows through gravitational collapse and structure formation. As gas collapses to form galaxies, gravitational potential energy converts to kinetic energy and eventually radiation, representing information processing at cosmic scales. Some researchers explore whether information-theoretic constraints limit how quickly structure can form, or whether information-theoretic perspectives reveal new principles governing cosmic evolution. Applying these abstract frameworks to concrete observations like James Webb's remains challenging but potentially illuminating. The philosophy of science reminds us that observations never uniquely determine theory, as multiple theoretical frameworks might account for the same data. The history of science shows many cases where anomalous observations initially seemed to threaten prevailing theories but were eventually accommodated through refinements rather than revolutionary replacements. Equally, history contains cases where persistent anomalies ultimately demanded paradigm shifts. Whether James Webb observations herald a major revision of cosmology or will be absorbed through incremental improvements remains to be seen, highlighting the uncertain nature of scientific progress. Scientific revolutions, famously analyzed by philosopher Thomas Kuhn, occur when accumulating anomalies render prevailing paradigms untenable, forcing adoption of new frameworks that reinterpret observations. The lambda cold dark matter model has successfully accommodated vast amounts of data, suggesting robustness. However, if James Webb anomalies prove irresolvable within this framework, despite earnest theoretical efforts, they might eventually trigger a paradigm shift. The threshold for such shifts isn't purely empirical, but involves community judgments about theoretical elegance, explanatory power, and practical utility, making the trajectory of cosmology somewhat unpredictable. The sociology of science acknowledges that scientific progress involves human communities with particular cultures, institutions, and incentive structures. Large collaborations, funding patterns, and career pressures influence what questions get asked and what theoretical avenues receive attention. The enormous investment in lambda cold dark, matter-based simulations and theoretical frameworks creates momentum favoring its preservation, potentially delaying recognition of fatal flaws if they exist. Conversely, the excitement around James Webb discoveries and the career benefits of proposing novel explanations might lead to premature abandonment of successful frameworks. Navigating these sociological factors while pursuing truth represents an ongoing challenge. The interplay between observation and theory ideally involves mutual constraint, with observations testing theoretical predictions while theory guides observers toward promising targets. James Webb observations were enabled by decades of technological development, motivated partly by desire to test cosmological models. Now, these observations challenge models in unexpected ways, likely motivating new theoretical developments and suggesting future observational priorities. This back and forth represents healthy scientific progress, even if the path forward seems uncertain. Statistical methodology plays crucial roles in interpreting observations and assigning significance to apparent tensions. Choices about how to quantify uncertainties, combine different datasets, and evaluate model agreement affect conclusions about whether anomalies exist. Different research groups sometimes reach different conclusions from the same data due to methodological differences, highlighting the importance of careful statistical practice. As James Webb data accumulates, meta-analyses combining results from multiple studies while accounting for systematic uncertainties will prove essential for reaching consensus about what observations genuinely challenge existing models. Publication bias, the tendency for positive or surprising results to be published more readily than null results, might affect how we perceive the state of the field. If observations confirming standard models receive less attention than anomalous findings, the community's collective understanding might become skewed. Efforts to quantify this bias and encourage publication of all high-quality results regardless of outcome help maintain accurate assessment of where observations actually stand relative to theory. The role of skepticism remains vital for scientific progress. Extraordinary claims require extraordinary evidence, and initial reports of surprising phenomena deserve careful scrutiny before acceptance. Healthy skepticism motivates critical examination of systematic uncertainties, alternative explanations, and theoretical assumptions. At the same time, excessive conservatism might delay recognition of genuine discoveries. Balancing these concerns requires judgment developed through experience and engagement with diverse perspectives within the scientific community. The pace of discovery in the James Webb era contrasts with earlier periods when major observations occurred less frequently. The rapid accumulation of data enables quicker assessment of whether initial anomalies persist or disappear with better statistics, but it also challenges researchers' ability to thoroughly analyze each dataset before the next appears. This accelerated pace might help resolve tensions more quickly than past episodes, but also risks hasty conclusions before systematic effects are fully understood. Future facilities will provide crucial tests of whether James Webb anomalies reflect genuine problems with cosmological models. The Nancy Grace Roman Space Telescope will survey enormous areas of sky with sensitivity similar to James Webb, revealing whether rare, bright early galaxies represent statistically significant populations or merely the most extreme outliers. Ground-based, extremely large telescopes will provide spectroscopic follow-up and detailed characterization impossible from space platforms. Radio arrays will map neutral hydrogen and molecular gas in early galaxies, constraining fuel supplies and formation mechanisms. The combined results from these diverse facilities should clarify the nature and severity of current tensions. Theoretical progress will require both refinement of existing models and exploration of genuinely new ideas. High-resolution simulations pushing to earlier times and smaller scales will reveal whether known physics, computed more accurately, can account for observations. Simultaneously, creative theoretical work exploring modified physics, alternative initial conditions, or entirely novel frameworks remains essential for ensuring we don't miss potential solutions by looking only in familiar places. Balancing these approaches demands diverse research strategies across the community. The time required to resolve current tensions remains uncertain. Some past apparent cosmological crises resolved quickly once key observations or theoretical insights emerged, while others persisted for decades. The Hubble tension, now roughly a decade old with multiple independent confirmations, illustrates how some discrepancies resist easy resolution. Whether the James Webb early structure observations follow a similar trajectory or find explanation more readily depends on whether they point to subtle astrophysical misunderstandings or something more fundamental. The significance of these questions extends beyond academic curiosity. Understanding how the universe evolved and whether our physical laws capture reality completely bears on humanity's place in the cosmos and our ability to comprehend nature. Throughout history, cosmological discoveries have reshaped philosophical and cultural worldviews, from recognizing Earth's motion to discovering cosmic expansion. While current tensions may or may not herald comparable revolutions, they remind us that our understanding remains provisional and incomplete. The beauty of science lies partly in its capacity for self-correction. When observations conflict with expectations, the framework demands taking observations seriously and revising theories accordingly. This mechanism, operating over decades and centuries through collaborative effort across generations of researchers, has built our current understanding and will guide us toward whatever picture ultimately accommodates all available evidence. The process involves uncertainty, false starts, and persistent puzzles, but it constitutes our most reliable method for uncovering how nature actually works. For now, the James Webb Space Telescope continues observing, accumulating data that will occupy astronomers for years as they extract its full scientific value. Each new observation refines our picture of the early universe, sometimes confirming expectations, sometimes delivering surprises. Theorists work to explain findings within existing frameworks while exploring alternatives. The community debates, checks calculations, proposes new tests, and gradually builds consensus about what observations genuinely challenge our understanding versus what reflects misinterpretation or systematic error. The ultimate resolution might vindicate lambda cold dark matter with only minor modifications, reveal the need for significant revisions to dark matter or dark energy physics, expose problems with our understanding of galaxy formation while leaving the cosmological framework intact, or point towards something more profound that current discussions haven't yet imagined. Scientists navigate this uncertainty with a combination of rigorous analysis, creative thinking, and patience to let evidence accumulate rather than rushing to premature conclusions. Whatever emerges, the journey itself advances knowledge. Even if current tensions ultimately dissolve into refined versions of existing theories, we will have learned something about the early universe, pushed observational and theoretical techniques forward, and deepened our understanding of cosmic structure formation. If tensions instead require major theoretical revisions, we stand at the threshold of discoveries that will reshape our cosmic worldview as profoundly as any in history. The questions raised by James Webb observations tap into the fundamental human drive to understand our origins and the nature of reality. From ancient mythologies explaining creation to modern cosmology reconstructing the universe's history from physical evidence, humanity has persistently sought to comprehend the cosmos. Contemporary cosmology represents this quest's latest chapter, armed with powerful telescopes and sophisticated theories, but still confronting mysteries that humble our understanding. As we peer deeper into space and further back in time, approaching closer to the universe's beginning, we probe regimes where our theories face their most stringent tests. The earliest epochs witnessed physical conditions never repeated since and never reproducible in laboratories. Understanding this era requires extrapolating physics across enormous ranges of energy, density, and temperature, a bold enterprise inevitably fraught with uncertainty. That our models work as well as they do testifies to physics' power, while the tensions now emerging remind us that nature always retains capacity to surprise. The collaboration required to address these questions spans continents, disciplines, and generations. Engineers design instruments decades before they operate. Observers painstakingly calibrate detectors and analyze data. Theorists develop mathematical frameworks and run simulations on the world's largest computers. All contribute to the collective endeavor of understanding cosmic history. This collaborative nature makes modern cosmology simultaneously humbling and inspiring, demonstrating what humanity can achieve through sustained cooperative effort toward shared intellectual goals. Looking ahead, The next decade promises remarkable opportunities to test our cosmological understanding. Multiple facilities across the electromagnetic spectrum will observe early galaxies with unprecedented sensitivity. Our gravitational wave detectors will probe black hole populations back to early times. Improvements in computing will enable ever more realistic simulations. New theoretical ideas will emerge from young researchers bringing fresh perspectives. The combination should clarify whether current tensions represent genuine crises or passing confusions. Regardless of specifics, cosmology will continue evolving as observations push understanding forward. The field has repeatedly demonstrated resilience, adapting to accommodate unexpected findings while preserving successful elements of previous frameworks. Lambda, cold dark matter itself, emerged through this process, synthesizing ideas about inflation, dark matter, and dark energy into a coherent framework matching diverse observations. If it requires modification or replacement, whatever succeeds, it will emerge through similar integration of new data with theoretical innovation. The story of how we came to observe distant galaxies that challenge our cosmic models itself reflects scientific progress. A century ago, we barely understood that galaxies exist beyond our Milky Way. Half a century ago, we lacked clear evidence for dark matter or cosmic acceleration. 2 decades ago, the first galaxies remained beyond observational reach. Each advance built on previous discoveries, enabling new questions to be asked and new puzzles to emerge. Today's tensions may seem frustrating, but they arise only because we've achieved sufficient understanding and observational power to recognize them. In this light, the anomalies observed by James Webb Space Telescope represent success as much as challenge. We've developed theories precise enough to make detailed predictions about the early universe. We've built instruments capable of testing those predictions. We've discovered that reality doesn't quite match expectations in ways subtle enough that detecting the mismatch required cutting-edge observations. This situation invites refinement of our understanding, offering opportunities for discovery that drive science forward. The questions remain open. Do fundamental constants vary? Does dark matter behave unexpectedly? Did the early universe expand differently than we believe? Are galaxy formation processes more efficient than models suggest? Or do systematic observational uncertainties explain apparent tensions? The answers will emerge through continued observation, careful analysis, creative theorizing, and the collaborative efforts of researchers worldwide pursuing understanding of our cosmic origins. Future astronomers, looking back at this era, may regard current tensions as critical clues that led to breakthrough understanding, or as misinterpretations eventually resolved through better data and refined theory. Either way, this moment of uncertainty and active investigation represents cosmology at its most vital, grappling with observations that challenge understanding and thereby driving the field toward deeper truths about the universe we inhabit and our place within its vast history.